In this web clip, we will discuss waves and their general properties. We will do so by first asking and answering 4 basic questions that allow us to introduce some general concepts. The first and most obvious question is, what is a wave? Well, a wave is something that oscillates in space and time. Oscillations in time, you know from the previous lecture, where we, for instance, discussed the harmonic oscillation. And now we also have something that varies with space. And that something, indicated here by psi, can basically be anything. It depends on the system, right? It can be an oscillation in a rope. It can be something like acoustics. But it can also be, for instance, an electromagnetic wave that we deal with in optics. So a wave, something in space and time. And the second question is, what is a traveling wave? Well, a traveling wave, as you could imagine from the name, is a wave that travels in space. So it's a certain pattern that either travels to the right or travels to the left. And the third concept is an harmonic or periodic wave. Well, a harmonic or periodic wave is like the harmonic oscillator, something that oscillates with a fixed frequency and hence oscillates forever. And this pattern can again move to the right or move to the left if you have a harmonic traveling wave. Then the final concept is a standing wave. And a standing wave is, as the name already suggests, a pattern that oscillates but doesn't move. So it stands still in place. An example thereof is, for instance, a vibrating string of a guitar. This slide demonstrates the nature of a traveling wave. So a wave that travels, in this case, from the left to the right, and in this case, it's a pattern that retains its shape, so that's dispersion free. And so the question we address is, which equation do you use to describe this traveling wave? And this is the form of the traveling wave. Right? It's a pattern that changes with position and with time in a very special way, namely in this way. So if you have a wave that travels to the right, as in this case, it has this form. But that's not an equation, or at least it's a functional form. We look for a equation of motion, like you have F is m times a in mechanics. So you look for something with derivatives. And derivatives of this function psi are somewhat complicated in the sense that the function depends on 2 variables, and that's why we will introduce a concept which is called the partial derivative, indicated by these curly deltas. And with the partial derivative, we mean the derivative of the function, but then keeping all other variables fixed, so at fixed time. So using this concept of partial derivative, you might think that you already get an equation of motion if you relate the partial derivative in space and in time by a prefactor of the form 1 over v. So you might think this is a proper equation of motion, but in fact it's not, for 2 reasons. One is you have this nasty plus or minus sign here, which complicates things. And the second is you have a first derivative in time, and that is typically not so physical. So this is not the right equation of motion. The right equation of motion for a wave you get if you take second order partial derivative. So if you try to relate the second order partial derivative in space and in time, and you notice there is a prefactor 1 over v squared both for the rightward traveling wave and for the leftward traveling wave. So this is the wave equation that describes the dynamics of a wave. Now there is one important principle that I still want to explain, the so-called superposition principle. And the idea is as follows. Suppose you have two solutions, psi1 and psi2 of this equation. Then, if you look at a linear combination of these two solutions, alpha psi1 plus beta times psi2, this is also a solution. And the reason is that if you take derivatives of this solution, then you can commute derivatives and products. So you can rewrite this thing as alpha times the partial derivative psi1 plus beta times the partial derivative psi2. And this doesn't only apply to first order partial derivatives, but also to second order partial derivatives. So this superposition principle tells you that you can use any linear combination. And that, for instance, also means that if you have a wave traveling to the right, and if you have a possibly different wave pattern traveling to the left, these guys will cross unperturbed, interfere when they cross, but after crossing, they retain their shapes. They do not interact. So let's clean up the slide. We've demonstrated two important ideas. First, that waves are described by the so-called wave equation, which relates the second order partial derivative in space with the second order partial derivative in time. And second, that this equation obeys the superposition principle, which means that if psi1 and psi2 are solutions, then also this linear combination is a solution. And the consequence thereof is that individual waves do not interact. If you have a wave traveling to the right and one wave to the left, they will interfere when they meet, but afterwards they will pass on unperturbed. An harmonic or periodic traveling wave is a wave that oscillates at a fixed frequency and therefore oscillates forever. And in this movie, you clearly see the link between, on the one hand, uniform circular motion, on the other hand, the harmonic oscillation, which basically is a projection of the circular motion, and finally, the harmonic traveling wave, which is like an harmonic oscillation that moves away in space. Now, the way to describe this harmonic oscillator or this harmonic traveling wave, you probably still know from secondary school. And in secondary school, in the way I wrote it, you use three parameters, namely the amplitude of the wave, the wavelength lambda of the wave, and the oscillation period capital T of the wave. At university, we tend to use different symbols, and you better get used to it because we will use them quite extensively during the course. And these different symbols are this K and omega, which replace lambda and capital T. And the relation between these properties, parameters, is as follows. K is the wave vector, and the wave vector K is 2 pi over lambda. It's the oscillation expressed in radians per unit length. Omega is the angular frequency. It's related to the frequency in cycles per second by multiplying by 2 pi, or to the oscillation period as omega is 2 pi over t. And the combination of these two gives you the propagation speed v, which you might remember as the product of frequency times lambda, but you can also write as the ratio between omega and k. Earlier, I mentioned the superposition principle. This movie demonstrates that principle. It demonstrates that a standing wave can be interpreted as the superposition of two traveling waves. One traveling to the right, and another one with equal amplitude traveling to the left, here indicated with blue and red. If you want to derive the mathematics of this superposition, you basically have to add a wave that travels to the right with a second wave of equal amplitude that travels to the left. And if you do the math properly, you find that this is the outcome of the superposition. It is a wave that oscillates in time, but has a fixed spatial profile indicated here. And you also see, for instance, that if these waves interfere constructively, the amplitude is 2 times a. If they interfere destructively, the amplitude is 0. And if you wonder, how can I remember this equation? Then it's based on the following math. It's based on the idea that if you add cosine, 2 different cosines, then the addition of these cosines can be rewritten as the product of the cosine of half the difference of the angles multiplied by the cosine of half the sums. And this prefactor 2 is obvious, because if you have equal angles, 1 plus 1 is 2, and these factors you can also remember, hopefully, because equal angles, again, is constructive interference, and that means that this combination is just 0, and the cosine of 0 is 1. So, sum of 2 traveling waves yields a standing wave of this form. This slide shows 3 examples of a traveling wave. So basically of this variable psi that I mentioned in the description. And the first is a transverse wave in a rope. If you wiggle a rope, what wiggles? The answer is not so complicated, I hope. What wiggles is the transverse position of the rope, which you, I guess, typically will indicate with y, transverse displacement, instead of psi. And this transverse displacement moves in position and, of course, also in time. A second example is an acoustic wave. What wiggles, what oscillates, what moves in an acoustic wave? Sound. And thinking of sound, you might know that sound means that things move in a longitudinal direction. So if you have a sound wave in air, the air moves to and fro from the source to the observer. So we are talking about something which you would call displacement and might indicate with psi or phi or whatever symbol you would like. So that's one way to indicate the oscillation in an acoustic wave. You could also think of other variables that change. Acoustics also means that the pressure changes with position in time. It also means things get compressed. So the density changes with position and time. And obviously, all these oscillations are related to each other, and you can use one variable or the other depending on your choice. Well, finally, the final example is the one we'll use extensively in optics. An optical wave, as you might know, is a particular electromagnetic wave. So what oscillates here is the electric field as a function of position, the magnetic field as a function of position, and it's a transverse wave. So if things move in a particular direction, k vector, the wave vector, then the electric field is transverse to this k vector in this direction, and the magnetic field is transverse to the wave vector in this direction. And actually there is a relation that we will encounter later on, which is based on Maxwell equations, and that relates the magnetic field to the electric field and the wave vector in this form. But this you don't have to know for now. That's the course on electromagnetic fields in the spring semester. Earlier, I mentioned the wave equation as a means to describe the dynamics of a wave, but I didn't derive that equation. So let's do that now for a particular case of a transverse displacement in a rope. A transverse displacement that we will indicate not with the psi, but with the displacement y as a function of position along the rope, x, and time. So the first question you will ask yourself is, what does the dynamics in this rope depend on which parameters? And if you think about it, I can think of two parameters. One being the tension in the rope, so the pulling force on the rope. If I pull hard on the rope, I expect the wave to move faster than if there is less tension in the rope. The second parameter is the mass of the rope, and in particular the mass per unit length, which I'll indicate with mu. So to derive the dynamics of a wave in a rope, what I will do is I will look at dynamics of a particular segment of length delta L. A segment here, but it could also be a segment here or a segment there. And I will describe the dynamics of these segments as you do in classical mechanics by the equation F is m times a. M being the mass of this segment, delta m, so mu times delta L, and a being the acceleration of this segment, so basically the second order derivative of the displacement with time, which we have indicated as the partial derivative with time. So the most complicated quantity in this expression is F. What is the force on each of these segments? Well, I already mentioned the pulling force, the tension in the rope. But if you look at the segment, you'll notice that the pulling force is both on the left of the segment and on the right of the segment, and that the net pulling force will depend, of course, on the tension, but also on the slope of the rope, or in other words, on the derivative of y versus position. There's a component on the right which will depend on the slope at position x plus delta x, the slope on the right, and there is a similar component of the force in the other direction on the left hand side of the rope. And so if you combine these two, you can rewrite this as F0 times the second derivative of y versus position times delta L. So now we combine everything into one equation, F times second derivative with position for a particular segment is m times a, and m was this guy, and a was this guy. If we divide finally by delta L and move one of the two quantities to the other side, we get as final result this thing, which if you compare it with the general form of a wave equation, I mean, this is a wave equation, and the comparison that I mentioned shows you that the speed of the wave v squared is f0 over mu. So a very nice result, which indicates that the wave equation is indeed the equation to describe the dynamics of a wave on a rope, and the speed of propagation of this wave is the speed squared is proportional to the tension in the rope and inversely proportional to the mass per unit length. Thank you for your attention.